And let's see, Josh, remind me of your topic. It is...
it's similar to Daniel's.
Similar. Neural network talk. Okay.
Yep.
I was about to say that, and then I thought, no, we already had the neural network talk, but we're going to have another one. So
Part 2.
It threw me off. Okay, great.
Okay. Okay. Hi, everyone. My name is Josh Anderson. I work at Southwest Research Institute, and today I'm going to be talking about our recent efforts to take a neural network and kind of put that onto a space-grade FPGA in the hopes that we could eventually fly this thing and use it in space. So if this sounds familiar, this is actually the same project that Daniel presented about. His presentation focused more on architecting the network and designing the neural network, while mine is going to focus on taking that network and then putting it onto an FPGA. So I apologize if these slides, Daniel already presented them, so I'll go through them real quick. But kind of the whole goal of the project was to take mass specs instrument data and figure out a way that we could do something with all of the data that's producing. So it produces about 80 megabytes per second, and there's no possible way that you could downlink all of that and send it to the ground. So what we did was we developed a neural network to kind of train it and compress the relevant parts of the data and only downlink that part of the data. And then the final objective, which was my part on the project, was to take that network and then put it onto an FPGA so that eventually we could fly this thing and use it. Okay, so I think Daniel already presented this slide, but just a quick refresher on deep learning and neural networks and AI. I know there's a lot of buzzwords about this stuff. But a convolutional neural network is really simply, it's a deep learning model, and there's many different flavors and types of neural networks, ranging from just a few layers deep to hundreds of layers deep. Our network on this one, I think, was around 20 layers, and they have many applications from like image processing, object detection, what we're doing, which is one-dimensional data, analyzing that. And it kind of seems like magic a lot. You hear these buzzwords, and you give it a bunch of data, and then it kind of spits out an answer, and you're like, how did it do that? But when you go down and you dig down, really all it is, kind of as the name suggests, it's just matrix convolutions. That picture there in the bottom right kind of tries to say what's going on there. So you can see it's kind of just a convolution over the input with some kernels, and you end up with your output, and you kind of train it to tell it what you want it to do. So a question that kind of comes up is, why do you want to do this on an FPGA instead of like a CPU or a GPU? And the main thing really is that FPGAs are really commonly used in space. They have a lot of heritage. There's rad-hardened FPGAs that have been flown before, like the Vertex 5, which is what we were kind of targeting for our project here. They also offer lower power consumption in comparison to like the GPUs that we use on the ground today for most of our machine learning applications. And then also, if you tried to run like a neural network like this on just like a CPU, it would just take forever just because it's just sequential. You're doing all these multiplications and additions, and it would just take forever. So FPGAs, the parallel computing power that they offer is really beneficial for what we're doing. I think Daniel already presented this slide, but this is just the basic high-level overview of the network that we have. You can see there's a bunch of different size layers, a few different convolutional layers. And the key thing about this network architecture was that it was optimized to be put onto an FPGA or something that's more resource constrained. So like typical weights are, you can see the original weights were over 1 megabit of weights, which would be like really hard to store on a space-grade FPGA. And so with this new network architecture, we were able to reduce the weights to around 230 kilobits, which is very, very important. So now getting into more of the details of what I did on the project. So I'm more of a software developer. I'm not an FPGA developer by any means. So my first approach to put this thing onto an FPGA was very, I guess you could say, simple-minded. Just kind of tried to lay out every single connection and multiplication onto the FPGA all in parallel at one time. And so you can kind of see the code there. It's very redundant. You can just see it's like, it doesn't look pretty. What we did was we architected one very simple layer, It's just one layer, and it only had 32 inputs and 16 filters. And that one layer filled up the entire Vertex 5 FPGA. So it was over 100% utilized. We tried a few different things. We tried moving to fixed point, reducing the number of bits that we were using on our inputs, and just nothing was going to be able to, there was no way we were going to be able to fit this thing that has over 20 layers, our final network. So we had to explore other solutions, which is when we started talking to Division 15, some of the FPGA developers over there. They were considering using this system on a chip from Xilinx, the Zinc. And what it is, it has an FPGA, a programmable logic portion, and a programmable system, an embedded processor. And what that allowed us to do is use this tool from Xilinx called SDSoC, which stands for Software Defined System on a Chip. And what that allows you to do is basically write your C and C++ code, which we're all familiar with, and then what it does is it takes that code and synthesizes it onto the programmable logic of your system on a chip. So you can kind of see the diagram there on the right. You have your programmable system, which would be like your processor. In the Zinc, it has 2 ARM processors on there. And then your programmable logic, which would be like the FPGA portion. And so what we did was we wrote C code to synthesize onto the programmable logic. And then getting into more of the details, on the upper right there, you can see a diagram of the Zinc UltraScale, which is the chip that we used. It's got 2 ARM processors, a bunch of I/O, some memory, and then at the bottom is the programmable logic, which has slices like DSP slices, which are used for digital signal processing. So it contains built-in multipliers and adders for doing your, which are really handy for like convolutions, which is what we're doing with the neural network. And then it also has some memory on the programmable logic as well. So what we did, now we do realize that the whole goal here is to put it onto a space-grade FPGA, and this isn't currently available in like a rad-hard version. So what we kind of tried to do was model it in a way that we could eventually move the algorithm and the approach to like a Vertex 5 or something that's flown in space before, so without a system on a chip. So what we did was we wrote this, this convolutional loop. You can kind of see some of the code there at the bottom. It's kind of a mess, a bunch of loops, and it's not very pretty to look at. But it's kind of, the idea is you call this function over and over again to perform your convolutions, and then you synthesize that single function onto the logic, and it takes up a very small amount of space in your FPGA. So here's the results of what we did. You can see the utilization in the bottom row of the table. We were very, very underutilized, the highest portion being your block RAM, which was about 40% utilized. The reason for this was because we actually stored, I know I mentioned in the beginning, we had about 230 kilobits of weights and biases, which the neural network uses. So we were storing that on the programmable logic itself. So that's where that high number comes from there. But everything else, like your flip-flops and your lookup tables, very, very underutilized. So we were pretty pleased with these results. And this is the one-dimensional network that we were using on the ground. So then after that, we decided to do some real small experiments looking at 2-dimensional network architectures. So instead of a 1-dimensional input like we had with the mass spectrometer data, maybe you have like a 2-dimensional image or a 2-dimensional video, and looking at how that changes the network size and how that changes what's happening on the FPGA. And so still pretty good results. You can see the lookup tables went up a little bit, but still we think it's possible that you could do something like this. And so I kind of mentioned before that we wanted to make sure that we could eventually put this without a system on a chip and do this only on an FPGA. So we kind of came up with a way that we could do this on an FPGA not using the Zinc and the SDSoC tools. So it's very similar, though. The big difference is the state machine there I have would kind of take place of the embedded processor. So it would kind of be in charge of taking your input stream, taking your weights and biases, which we are going to say that we could store off the chip somewhere and then fetch them from memory later. And then it kind of takes those and gives that to the DSP and the logic slices, which we kind of partition off for doing the main part of your computations there. So with the help of some guys in Division 15, the space FPGA developers, we were trying to extrapolate and see if this would even fit on a Vertex 5. And So if we assume, and we heard from the engineers there, that the DSP slices and the lookup tables are actually very similar between the Zinc and the Vertex 5. So if we assume that those are very similar, the utilization there would be about the same. And then we assume that we can store the weights and biases off the chip. We think that we could fit this onto a Vertex 5 using the hypothetical design. The only thing with this table is we're not really accounting for that state machine logic, which is fetching the inputs and kind of moving the data around. But in comparison to your multiplications and your additions that the convolutions are happening, that would take up a lot less hardware resources than those. So we're pretty confident that this would work. In conclusion, kind of touched on it, but we're pretty confident that we could potentially put this onto a space-grade FPGA like a Vertex 5 or something like that, and then we could use this network to compress data on board and process the mass amounts of data and then reduce the amount of volume that you need to downlink. And then kind of a separate thing was this SDSoC tool from Xilinx was actually very useful to prototype and kind of benchmark a design and see what kind of hardware resources it would take before actually going to an HDL like hardware like Verilog implementation before spending all the time there. And then next steps, of course, next logical step is to put this thing onto a Vertex 5 and then compare the speed and the scalability versus like a GPU, which is what we use here on the ground. And then, of course, improving the resource utilization because we were very close to 0% you saw on the results there. So there's a lot of unused resources that we could be taking advantage of and maybe improving the speed. And then another thing is looking at like 2D satellites data, maybe for images or videos. That's all I had.
Thank you. Any questions? No? Thank you. Oh.
No worries. Very interesting presentation. And I have one question is that suppose such a thing would go ahead and fly, how would you update your neural network during operations if it were like, if it was like stored on a spacecraft?
Right. I think the idea would be that you would do all of your training and developing of the neural network on data on the ground and kind of test it out and make sure that it functions very correctly there. I don't really think that we would have thought of any way to change it while it's flying. You know, you kind of do it in the ground and then launch it and not change it.
I just have a practical question. What was your experience, or how would you rate the ease of use on the Xilinx or Zinc software-defined system on the chip? You know, the development environment.
It was kind of a learning curve. It's a pretty new technology, so there's not a lot of support out there for it. There's some documentation, but there's not a big user base, really. But the tools themselves, there were a few, like, I guess, things that you kind of had to work around, but they were pretty good. So.
Thanks.